In the intricate world of artificial intelligence and neural networks, there's a fundamental concept that acts as a gatekeeper for information, deciding what gets passed on and what gets left behind. This is the role of an activation function. Think of a neuron in the human brain. It either fires or it doesn't. Activation functions bring this all-or-nothing non-linear behavior to artificial neurons, allowing them to learn complex patterns from data. Without them, a neural network would just be a simple linear regression model, unable to tackle tasks like image recognition or natural language processing. Today, we're diving into three of the most foundational activation functions: Sigmoid, Tanh, and the undisputed modern favorite, ReLU. Let's start with a classic, the sigmoid function. Its characteristic S-shaped curve takes any real number and squashes it into a range between 0 and 1. This is incredibly useful for binary classification problems, where the output can be interpreted as a probability. For a long time, sigmoid was the go-to activation function. However, it has a significant drawback known as the vanishing gradient problem. When the inputs are very large or very small, the gradient of the sigmoid curve becomes tiny, close to 0. During training, this means the network learns very slowly or stops learning altogether for those neurons. Next up is the hyperbolic tangent, or Tanh function. Visually, it looks a lot like the sigmoid function, but it squashes values to a range between 1 and 1. This simple change has a big impact. Because its output is zero-centered, the Tanh function often helps to center the data for the next layer, which can make learning a bit easier and faster than with sigmoid. However, it doesn't fully escape the vanishing gradient problem. Like sigmoid, the gradients at the extreme ends of the Tanh function are also close to 0, which can still slow down training in very deep networks. Now let's meet the current champion, the rectified linear unit, or ReLU. Its function is beautifully simple. If the input is positive, it returns the input. If the input is negative, it returns 0. This simple rule has profound consequences. ReLU is computationally very efficient because it only involves a simple max operation. More importantly, for positive inputs, the gradient is always 1, which means it completely avoids the vanishing gradient problem on one side. This allows networks to learn much faster and is a key reason why ReLU has become the default activation function for hidden layers in most deep learning models today. It introduces non-linearity while being incredibly effective and fast. So how do they stack up? Sigmoid is great for output layers, where a probability is needed, but suffers from vanishing gradients. Tanh is a zero-centered improvement, but still has gradient issues. ReLU is the fast, efficient workhorse that solves the vanishing gradient problem for positive inputs, making it the standard for most applications. The journey from sigmoid to ReLU reflects the evolution of deep learning itself, a continuous search for functions that allow us to build deeper, more powerful, and more efficient neural networks. Driving the AI revolution forward,